Look up on a clear night, far from the glow of any city, and you will see thousands of points of light scattered across the dark. Each one is a sun. Some are bigger than ours, some smaller, some older, some younger. And around an unknown but almost certainly enormous number of them, there are planets, worlds with mountains and oceans, and maybe, just maybe, something looking back. It is one of the most natural impulses a thinking creature can have, to look at that scattering of light and want to go there. To imagine climbing aboard a ship and simply flying toward the nearest star the way you might drive toward a distant mountain. And yet, when we actually sit down and do the physics, when we take seriously what space and time really are, what the speed of light really means, and what the universe is really doing on its largest scales, we run into walls that are not walls of engineering, but walls of law. Not we don't have the technology yet walls, but the universe itself will not permit this walls. Today, I want to walk you through why that is. Not to depress you, not to take the romance out of the night sky, but because I think the actual reasons are more beautiful and more strange than any science fiction shortcut could ever be. To understand why the stars are so profoundly out of reach, we have to start with something that sounds simple but is anything but. What are space and time, actually? For most of human history, space was thought of as a kind of infinite silent stage, a fixed backdrop against which the events of the universe played out. Time was thought of as a universal clock, ticking at the same rate everywhere, for everyone, always. This was Newton's picture, and it is still, frankly, how most of us walk around thinking about the world, because at the speeds and scales of everyday life, it works extremely well. But in 1905, a young patent clerk in Bern, Switzerland, sat with a puzzle that had been nagging at the edges of physics for decades. And he found that the stage and clock picture cannot be right. Albert Einstein started from a single, almost absurdly simple observation. The speed of light, measured by anyone moving at any speed, in any direction, always comes out the same. Roughly 300,000 kilometers every second. It does not matter if you are standing still or racing toward the light source in a rocket. You will always measure light traveling at that same speed. This seems like a small technical fact. It is not. It is a wrecking ball aimed at the classical idea of space and time as separate, fixed things. Here is why. Speed is just distance divided by time. If the speed of light must come out the same for every observer, no matter how they are moving, then something else has to give. Space and time themselves have to adjust, observer by observer, so that this one quantity, the speed of light, stays fixed. And that is exactly what Einstein showed. If you are moving relative to me, your clock, from my point of view, runs slower than mine. Your ruler, from my point of view, is shorter along the direction of motion than mine. This is not an illusion, not a trick of perception. It is a genuine fact about the structure of reality. Space and time are not separate, independent things. They are woven together into a single four-dimensional fabric that physicists call spacetime. And different observers moving at different speeds slice up that fabric differently into what they call space and what they call time. There's no universal agreed upon now spanning the universe. There is no single master clock. Every observer carries their own. Now, buried inside this theory, special relativity, as it's called, is a speed limit. Not a speed limit imposed by some cosmic traffic authority, but one built into the very geometry of space-time. As an object with mass moves faster and faster, the energy required to accelerate it further grows and grows, and as its speed approaches the speed of light, that required energy approaches infinity. To actually reach the speed of light, an object with mass would need an infinite amount of energy, which is another way of saying it simply cannot be done. Light itself can travel at the speed of light because photons are massless. But you, me, a spaceship, a coffee cup, anything made of matter is barred from ever reaching that speed, let alone exceeding it. This is not a limitation of rocket engines or fuel efficiency. You could have a propulsion system of literally unlimited power, and you would still asymptotically approach the speed of light and never quite touch it, because the very fabric of space-time resists it more and more fiercely the closer you get. This single fact, on its own, already tells us something sobering about interstellar travel. The nearest star system to our own, Proxima Centauri, is about 4.2 light years away. A light year is the distance light travels in a year, about 9.5 trillion kilometers. Even if we could build a ship that reached, say, 90% of the speed of light, an engineering feat so far beyond anything we currently have that it is almost a fantasy in itself, the trip would still take more than 4.5 years from Earth's perspective. And thanks to time dilation, a somewhat shorter time for the people on board. That's the nearest star. Our own galaxy, the Milky Way, is about 100,000 light years across. The nearest large galaxy, Andromeda, is 2.5 million light years away. At any speed less than light, and remember, we can never actually reach light speed, crossing these distances within a human lifetime, let alone within the lifetime of a civilization's patience and resources, becomes essentially impossible using any propulsion method that plays by the rules of ordinary physics. But it gets stranger because special relativity is really just the warm-up act. In 1915, Einstein extended these ideas into general relativity, a theory of gravity unlike anything that came before. Newton had imagined gravity as a mysterious force acting instantaneously between masses across empty space. Einstein showed instead that gravity is not a force at all in the traditional sense. It is the curvature of space-time itself. Mass and energy bend the fabric of space-time around them, the way a bowling ball placed on a stretched rubber sheet creates a dip. Other objects moving nearby don't feel a mysterious pull. They simply follow the straightest possible path through this curved geometry, and that path looks to us like an orbit or a fall. Earth doesn't orbit the sun because the sun reaches out and grabs it. Earth orbits the sun because the sun warps the space-time around it. And Earth is simply moving in a straight line through space that is no longer straight. This idea that space-time itself is a dynamical, flexible thing, not a fixed stage, turns out to matter enormously for our question about reaching the stars, because it means that space itself can stretch. And on the largest scales of the universe, it is stretching right now, everywhere, all the time. This brings us to the Big Bang. About 13.8 billion years ago, the observable universe was in an unimaginably hot, dense state, and it has been expanding and cooling ever since. This is not an explosion happening within space the way a bomb detonates within a room. It is space itself expanding every region of it, everywhere, simultaneously, with no center and no edge. Galaxies are not, for the most part, flying away from each other through space the way debris flies away from a bomb blast. Instead, the space between galaxies is itself growing, carrying the galaxies along with it. Like raisins in a rising loaf of bread, all moving apart from each other, not because the raisins are swimming through the dough, but because the dough itself is expanding everywhere at once. This gives rise to something called Hubble's law. The farther away a galaxy is from us, the faster the space between us and it is stretching, and the faster that galaxy appears to be receding. And here is the crucial, almost unbelievable point, because this is the stretching of space itself and not the motion of objects through space. There is no limit imposed by the speed of light on how fast this recession can appear to happen. Special relativity's speed limit applies to things moving through space. It does not apply to the expansion of space itself. So beyond a certain distance, a boundary cosmologists call the Hubble radius, galaxies are receding from us faster than light, not because they are breaking any law of physics, but because the space between us and them is stretching so quickly that light itself, chasing after them, cannot close the gap. To make this even more dramatic, in the late 1990s, astronomers discovered that this expansion is not just continuing, it is accelerating. Something is pushing space apart at an ever-increasing rate, something we call dark energy, and we do not fully understand what it is. But we can measure its effect with tremendous precision, and the effect is this. The accelerating expansion means that more and more galaxies are, as time goes on, crossing over that Hubble radius and becoming forever unreachable. Their light forever unable to reach us, our light forever unable to reach them. There is a cosmic horizon, much like the horizon around a black hole, beyond which we simply cannot ever send a signal, a ship, or even a beam of light. No matter how much time we're willing to wait, because the space in between is stretching faster than anything can cross it. This means something quite profound. The observable universe that we can, in principle, ever reach, ever touch, ever influence is shrinking in a meaningful physical sense as time goes on. Galaxies that are visible to us today, whose light left them billions of years ago and has only just arrived, may already be receding from us fast enough that we could never send a probe there, even traveling at the speed of light. We are, in a very real sense, on an island that is not fixed in size but is slowly and permanently losing territory to an ocean of space, expanding faster than any signal could ever cross it. Even within our own cosmic neighborhood, our local group of gravitationally bound galaxies, including Andromeda, we are safe from this effect because gravity holds us together tightly enough to resist the expansion. But beyond that gravitationally bound neighborhood, the vast majority of the universe's galaxies are, or eventually will be, permanently beyond any possibility of contact. So we have two enormous physical facts working against interstellar travel simultaneously. First, nothing with mass can reach or exceed the speed of light, which makes even relatively nearby stars, a handful of light years away, a journey of years or decades, even under best case, wildly optimistic engineering assumptions. Second, on cosmic scales, space itself is expanding and accelerating in that expansion, which means an enormous and growing portion of the universe is fundamentally unreachable no matter what technology you have, because the very ground you would need to cross is receding faster than you could ever cross it. Now, you might be thinking, but what about wormholes? What about warp drives? What about clever loopholes that let you cheat the speed limit without technically breaking it? This is where string theory enters the conversation, because it's in the realm of these highly speculative, deeply theoretical ideas that physicists have looked hardest for potential escape hatches. String theory arose from an attempt to reconcile general relativity, our theory of gravity and the large-scale structure of space-time, with quantum mechanics, our theory of the very small, the world of particles and probabilities. These two theories, each spectacularly successful in their own domains, essentially refuse to speak to each other when you try to combine them, producing nonsensical infinities. String theory proposes that the fundamental constituents of reality are not point-like particles, as the standard model of particle physics assumes, but tiny, vibrating, one-dimensional strings, or in more modern formulations, higher-dimensional membranes. Different vibrational patterns of these strings correspond to different particles. An electron is one note, a quark is another, a photon another still, all played on the same fundamental instrument. One of the strange and striking requirements of string theory for its mathematics to remain consistent is that it needs more dimensions of space than the three we experience. Depending on the version of the theory, this can mean 6 or 7 additional spatial dimensions curled up and compactified at scales so small, near the Planck length, about 100 billion times smaller than a proton, that we have no way of detecting them directly with any current or foreseeable technology. This is genuinely wild territory, and I want to be honest with you about where the science is solid and where it becomes speculative. The mathematics of string theory is elegant and in many ways deeply compelling, but it has not yet been experimentally verified, and it may be decades, or it may never be possible, to test some of its more exotic predictions directly. Within this landscape of extra dimensions, some physicists have explored the theoretical possibility of shortcuts through space-time, wormholes, which are solutions to Einstein's equations that connect two distant points in space-time through a kind of tunnel, potentially allowing travel between them that is much shorter than the straight-line distance through ordinary space. It's a genuinely fascinating idea, and it comes directly out of general relativity's own mathematics, not just science fiction imagination. But here is the sobering reality. Every known solution that produces a stable, traversable wormhole, one you could actually fly a ship through and survive, requires what's called exotic matter, matter with negative energy density. As far as we currently understand physics, this kind of matter, in the sustained large quantities that would be needed to hold a wormhole open, does not exist and may not be able to exist in any meaningful, usable amount. Quantum effects can produce tiny, fleeting regions of negative energy, but nowhere near what would be required to keep a wormhole from collapsing the instant something tried to pass through it. Similarly, ideas like the Alcubierre warp drive, a mathematically valid solution to Einstein's equations that involves contracting space-time in front of a ship and expanding it behind, effectively carrying the ship along in a bubble without the ship itself ever locally exceeding the speed of light, sound like a clean loophole. And in a sense, they are a genuine loophole in the letter of the law, since nothing within the bubble is moving faster than light relative to its own local space-time. But when physicists work out what it would actually take to create and sustain such a bubble, the energy requirements come out to be, in most calculations, comparable to or exceeding the mass energy of entire stars, or even requiring, again, exotic negative energy matter that we have no evidence exists in usable form. Some newer proposals have tried to reduce these energy requirements, and it's an active, genuinely interesting area of theoretical research, but we remain enormously far from anything resembling a workable warp drive, and there is no guarantee the physics will ever cooperate. So even string theory and general relativity's most exotic, most speculative offspring, wormholes and warp bubbles, run headlong into requirements that, as far as we can tell, the universe simply does not provide the ingredients for. This is not a failure of imagination. Physicists have imagined these things in exquisite mathematical detail. It is a failure of the universe to supply the exotic materials and energies these solutions demand. Now let's bring aliens into this picture, because this is where all of these threads, relativity, cosmic expansion, and the sheer scale of the universe, collide most poignantly with our hopes and our curiosity. The Milky Way alone contains somewhere between 100 billion and 400 billion stars, and we now know from decades of exoplanet discoveries that planets are extremely common, essentially the rule rather than the exception. Statistically, it would be strange if Earth were the only place where life, or even intelligent life, arose. This tension between the seeming statistical likelihood of other intelligent civilizations and our total lack of contact with any of them is known as the Fermi paradox, named for physicist Enrico Fermi, who is said to have asked simply, "Where is everybody?" There are many proposed resolutions to this paradox, ranging from the idea that intelligent life is actually far rarer than we assume, to the idea that civilizations tend to destroy themselves before becoming detectable, to more unsettling ideas about deliberate silence or avoidance. But everything we've discussed today points to a resolution that requires no catastrophe, no conspiracy, no rarity of life at all. The sheer geometry and physics of the universe may make contact between civilizations extraordinarily difficult. Even if the universe is teeming with life, if a civilization exists 1,000 light years away, any signal we send would take 1,000 years to arrive, and any response would take another 1,000 years to return. A conversation would unfold across millennia. If a civilization exists far enough away beyond that cosmic horizon we discussed, driven by the accelerating expansion of the universe, then no signal, no matter how patient we are, no matter how long we wait, could ever reach them or ever reach us from them. Some fraction of the civilizations that may exist in this vast universe are not silent by choice or by tragedy. They are silent because the universe itself has placed them permanently beyond the reach of any possible message. And even setting aside the very edges of the observable universe, the practical difficulty of interstellar contact within our own galaxy is staggering. Even a message traveling at the speed of light, the fastest anything can travel, takes tens of thousands of years to cross the Milky Way. A civilization would need to persist in a technologically capable and attentive state for time spans far longer than the entire span of recorded human history, just to have a reasonable chance of sending and receiving a single meaningful exchange with a neighbor on the far side of the galaxy. Add to this the difficulty of physically traveling those distances, the same speed limit, the same energy requirements, the same absence of viable wormholes or warp drives, and you start to see why, even in a universe that might be absolutely brimming with life, actual physical contact between civilizations, ships meeting ships, boots touching alien soil under a foreign sun, may be vanishingly rare. Not because life is rare, but because space and time themselves conspire against it. I think it's worth sitting with why this matters, and why, to me, it isn't actually a sad story. When we first learned these facts, that we can never reach even our nearest stellar neighbors within a human lifetime using any physics we currently understand, that vast portions of the universe are permanently outside our cosmic horizon and always will be, that the elegant escape hatches of wormholes and warp drives seem to require materials the universe simply doesn't stock on its shelves. It can feel like a kind of imprisonment, like we've been placed in a beautiful room with the windows painted shut. But I'd encourage you to look at it a different way. The very fact that we, tiny creatures on a small rocky planet orbiting an unremarkable star, have been able to work out these truths to derive from pure thought and careful observation that space and time bend, that light has an absolute speed limit, that the universe itself is stretching and accelerating, that there might be extra dimensions curled up at scales smaller than we can currently probe. This is itself one of the great triumphs of the human mind. We may never physically stand on a planet orbiting Proxima Centauri, but we have, in a very real sense, reached out and touched the fundamental architecture of the cosmos with our equations and our instruments, and that is its own kind of arrival. There is also this: the impossibility of easy interstellar travel does not mean the impossibility of interstellar knowledge. Telescopes like the ones we are now building and launching can, and increasingly do, analyze the atmospheres of planets around other stars, searching for the chemical fingerprints of life, oxygen, methane, other gases that, in combination, are difficult to explain without biology. We may, within decades, gather strong evidence for life elsewhere in the universe without ever sending a single spacecraft there. We can learn what's out there even if we cannot go there, and knowing may turn out to be almost as profound as going. And perhaps most importantly, none of what I've described today is a final, unquestionable verdict. Physics has surprised us before, dramatically and repeatedly. A century ago, the idea that space and time were flexible, that black holes existed, that the universe had a beginning at all, would have sounded like science fiction to most physicists. String theory itself, incomplete and unproven as it is, continues to reveal strange and unexpected mathematical structures. Extra dimensions, dualities between seemingly unrelated theories, hints of new symmetries, and it's entirely possible that a deeper understanding of quantum gravity, still to come decades or centuries from now, will reveal loopholes we cannot currently imagine, the way general relativity itself revealed loopholes Newton could never have conceived of. I am not going to stand here and tell you interstellar travel is forever, permanently, absolutely impossible for all future science. What I can tell you with real confidence is that it is impossible within the physics we currently understand, using energy sources and materials we know to exist, and that closing this gap would require discoveries as revolutionary as relativity itself was in its own time. So, when you look up at the stars tonight, I don't want you to feel small in a diminishing way. I want you to feel small the way you feel small standing at the edge of an ocean or looking up into a cathedral ceiling, small in a way that opens something up inside you rather than closing it down. Those points of light are not just distant and unreachable. They are the visible edge of a vast, dynamic, stretching, curving structure that we have only just begun to understand, a structure whose basic grammar, the grammar of space, time, energy, and matter, we have somehow, against all odds, managed to read. We may never walk beneath an alien sky, but we have done something almost as remarkable. We have figured out, sitting here on this one small world, exactly why we can't. And in doing so, we have mapped out the shape of the universe itself. Its beginning, its expansion, its ultimate horizons, and the deep laws that govern every star we will ever see and every star we never will. That to me is not a story of limitation. It's a story of extraordinary reach, achieved not with our bodies but with our minds.